Assalamu alaikum wa rahmatullahi wa barakatuh. This is Saud. Today, inshallah, we'll perform an experiment on the DC shunt motor. Before we start, let's review together what we've taken before on the principle of generation. So, in order to generate, we have to have three conditions. The first one is magnetic field, the second one is coil, the third one is movement. The magnetic field can be achieved by using natural magnet, permanent magnet, or temporary magnet. Temporary magnet is an element that is able to be magnetized if the electric current passes through it. Like this example. If we have an iron screw and we connect this iron through a coil to a battery, if we turn on the battery, the electric current will pass and these clips will be attracted. Okay, moving on. The below figure will illustrate the three conditions. We have a flux going from the North Pole to the South Pole. We have the coil and we have the rotation, which is clockwise. Now, what I have to know is the current movement. So let's agree that there is two current movement. In, the current will go in, and out, the current will be out of the picture. So, according to Fleming's right hand rule, if we have a flux going to the left and rotation going up, the current movement will be in. So, in the pink wire here, the current movement will be in. If this wire comes to a vertical position and goes down, it will follow this hand. So I have flux, same direction, the coil is going down, and as I can see that the current movement is out. So the same wire, which is this one, the pink wire, will expect two current movement. This two current movements will produce an AC signal for us, where here the positive signal, where the current starts from here going up to here, and the negative signal when the same wire, this one, going from here to here, and at this vertical position I will get 0 here and 0 here. So the AC generation, the generation itself is AC by default. Now, if I want to keep the generation as an AC generator, I have to connect the termination of the coil to something called slip ring, and that's it. But if I want to change my generation to DC, I have to use something called commutator. The commutator guarantees that the movement of the current will be the same for each brush. So, for example, this brush will take only right now the red wire. After a while, it will come to an air gap and the blue wire will be conducted here. The blue wire, after a while, it will go up, and the red wire right now is going up. So this brush will take only the wires that is going up. So the movement of current is in, and here it will be out. So the movement of the current generally will be clockwise. So it's only one direction, starting from 0, from here, going up, then 0 here, then again. So this is a DC direction because we didn't go to the AC, we didn't go to the negative, while the polarity of the wire will change. Now, if I connect multiple coils, what I will get is a DC waveform like this. If I increase the number of coils, I will get an AC waveform like this. So it will purify itself if we increase the number of coils. To compare between generators, I have to check the voltage regulation. The voltage regulation is the difference between the voltage or the generated voltage at no load condition and full load condition. A high percentage of the voltage regulation, that's mean I have poor voltage regulation, and the low percentage is a good voltage regulation. Since my machine is generator, I have to I produce electricity, so I have to connect electric load, such as resistor. Now, DC motor. We can define DC motor as a machine that converts electrical energy into mechanical energy. So, from the definition, we can know that the output is mechanical or rotation. I have to follow the same condition again. I have to have flux, which is here from north to south. I have to have coil. This is the coil. And 3, I have to have current or electricity. The current will be produced by this battery. So the armature here will be connected to a battery. Now, previously we were taking the output from the armature. Now we are feeding the armature by supply to run current through the coil. Now, according to Fleming's left hand rule, left, not right, using your left hand. If we have a magnetic field, if we have a magnetic field going to the right, and you have a current induced in N direction, you will have a force pushing this wire to go, pushing this wire to go up. If we have magnetic field going to this direction, and you have a current going to, out direction, you will have a force that is forcing the wire to go up. So now, since the force introduced, that means if you push something, that thing will move, right? So if we put a force or mechanical force on the wire will move. So, and this wire also expect a force on it, and it will be in opposite direction. So I will end up with a rotation. This rotation is the mechanical energy or the output of the motor. Let's take this circuit diagram. In our experiment, which is the shunt motor, I have to have the field coil or the stator connected in parallel with the armature. These resistors are in the circuit just to control the current or the amount of current produced. So I have to have supply parallel to the coil and parallel to the armature, as simple as this. So this is the shunt motor. If we can represent it like this, this is the coil or the field coil of the shunt, and this is the armature, these wires coming from the armature, we can say that, let me choose another color. Yes, we can connect those together and those together and connect it to power supply, and we will end up with a shunt motor. In the practical session, what we have to do, this is the armature. Change the color. This is the armature. This is the terminal to the armature, and this is the shunt coil, or the field coil, or the stator. Since I'm connecting them in parallel, what I have to do, connect 1 to 5 and 2 to 6, like this one, like the circuit. But in the lab manual, they are including the field rheostat. So what you have to do is just, instead of going here, just go here, like this one, from the coil to the resistor, and from the resistor to the armature. And that's it. Then you bring your DC supply to the armature, or to here, not different. Now we have a shunt motor. Okay. Since I have rotational output, I want to measure the speed or the revolution per minute. كم دورة في الدقيقة جالس يدور هالشافت هذا. Also another important factor is the torque, or the ability of motor to rotate something. If we can see the equation of the torque, we find that it's force multiplied distance, or Newton per meter, which is the unit of the torque. The force applied from by the motor to the shaft, and the length of the shaft. Also, another important thing is the speed regulation. We want to measure the speed at no load, no mechanical load, and full mechanical load, and we will see the difference between them. If the percentage is high, that means I have a poor speed regulation of that type of motor. If the percentage is low, that means I have a good speed regulation of that motor. Comparing to the generator, we compare it with the voltage regulation. If we can see the two important characteristics previously in the generation, we can see that they are the load, or R load, and the voltage. So both of them play a major role to determine if the generator is suitable for us or not. Now in the motor, the two important characteristics in the motor is the speed and the torque. Those two define the motor itself, or define the application of the motor, or define if the motor is suitable for us or not. This is the practical session. What we have to do is connect the DC supply 7N, this one, in parallel to the field coil, this one. The field coil will be connected in series with the field rheostat, and in parallel to the armature, which is this one. So, like, what's the benefit of the field rheostat? Take a look, please. If we are measuring the resistance of the coil, of the field coil, just of the field coil itself, it will be 367. But if we connect the field rheostat in series, look, I can increase the resistance. If I increase the resistance here, that means less current will flow we can measure the armature resistance by connecting the ohm meter to 1 and 2, the terminal of the armature. This is my connection. I have the supply connected in parallel with the armature, but in case of measuring the current, I will connect it to a meter. Then going back to 1, it will be the same, and the shunt field coil will be connected in parallel to the armature. The shunt field coil will be connected in series with the field rheostat. Since my machine is motor, what I have to do is connect a mechanical load, because the output of the motor is a rotation. So the mechanical load will be the dynamometer. What I have to do is connect the low power input to the supply here, okay, and adjust the load by this control knob. I have here a toggle switch to switch between the torque and the speed, and I have to make sure that the mode of this dynamometer is on the dynamometer, not a prime mover. Now, a couple of things before we start. First of all, I want to make sure that the field rheostat is at the minimum, because I want the field excitation current to be at the maximum. That's why I have to make sure that the field rheostat is 0 or at the minimum. Then I have to make sure that the load control knob is at the minimum to provide minimum starting load. I'll turn on the power supply, adjust the voltage up to 120 volts. Then I will see the speed by changing the toggle switch from torque to speed. Then, as it says by the lab manual, I have to adjust the field rheostat until the speed is 1800. So this is the field rheostat. Now, I will fill this table by measuring the current and the speed according to the torque. Now the current is 1.2 or 1.4, sorry, and the speed is 1800. Now I have to adjust the torque to 3 foot-pound per inch. Torque. Now you can see that the speed drops down. Whenever you increase the torque, the speed will go down. Let me see. 1752. And this is the table after filling it. We can see that there is an inverse relation between the torque and the speed. Whenever the torque increases, the speed will decrease. Also, if you increase the torque, the current will increase accordingly. But why we have a variation in the speed? Because we should have a constant speed, right? We're applying a constant voltage to the field coil and the armature, and since the speed is an armature voltage and flux dependent, we should get constant speed. The variation is due to the armature resistance. As you can see here, if you increase the torque from no load to full load, the current will increase. That means you're increasing the current here. So if you increase the current, the voltage drop across the armature resistance will increase, right? And since you're applying a voltage and you increase this one, the armature voltage should decrease. And since the speed is a function of the armature voltage, the speed will decrease.
This is the graph of the DC shunt motor, represent the speed versus torque. We can see it's a line, so it's nearly constant. And this is the equation of the speed regulation, and we can see that the speed regulation is 12.2, which is a good speed regulation. Now, what will happen if I start the motor with a maximum load, 12 pound force per inch? What will happen is the current will increase very quickly to overcome the mechanical load. So I will turn on the power supply, increase the applied voltage, and I can see that I reached to the 3 ampere, which is the maximum current drawn by the armature, when I reach 25 voltage with developed torque 2.6. We need 12 to overcome the mechanical load and rotate the dynamometer. So what will happen, I will use Ohm law to find the resistance. 25 divided by 3, this is the resistance, 8.3. And I will calculate the starting current if the full line voltage applied by the same concept. So the applied voltage 120 divided by the resistance to calculate the starting current. The resistance is 8.3. So the starting current to overcome the mechanical load is 14.4 ampere.